This second Optica online industry meeting starts in 5 minutes. Remember that as well as another 16 online industry meetings this year, some very important in-person summits are being prepared right now. Take advantage of early bird registration rates, which are even lower if you're an Optica corporate member. Here's an overview of what's to come.
Optica will bring together the brightest and best in Los Angeles. Corner, New York, Brussels, Glasgow, Sunnyvale, Paris, and Malaga.
Got my shades in the lab about 10:15. White coat cuff like a greaser again. Spinning that prism like a hubcap chrome, turning every photon into fuel I own. It's Photonics. Baby, 2026. Riding that light wave, doing new tricks. From the fiber in the ground to the chip in my hand, we make that sunshine jump on command. Yeah, Photonics. Baby, 2026. Tiny little wave got on a thumbnail chip. Makes your eyes look slow and stiff. Lasers in the toolbox, markers on the floor, drawing up a future through a tiny door. It's Photonics. They're Photonics. Riding that light wave, doing new tricks. From the fiber in the ground to the chip in my hand, we make that sunshine jump on command. Yeah, Photonics. Baby, Photonics. From a single red dot on a dusty bench to a whole wide world in a data trench. Flip that switch, see the spectrum spin like a jukebox jumping when the coins roll in. Oh yeah! Baby, 2026. Riding that light wave, doing new tricks. From the
It all will happen here at IX Campus Castle of Saint-Germain-en-Laye in Paris. See you then.
We're crossing boundaries, layer by layer. What stood apart now works as one. Built with precision, placed with intent, from separate parts to a single system. Heterogeneous integration, designed to perform. Built on silicon, extended beyond. Lithium, Batidium, falsified, quantum dot light, placed right on time. Lithium, Batidium, falsified, quantum dot light, placed right on time. Heterogeneous integration, not theory, not abstract. This is how photonics moves forward. Find out Tuesday, January 27.
Time to look ahead to the next Optica online industry meeting. On Tuesday, January 27th, we bring together industry leaders to discuss challenges ahead for heterogeneous integration. This is no longer an academic discussion. It's about what can actually be built to a deadline, tested and manufactured at scale.
Heterogeneous integration designed to perform.
We'll include perspectives from Lumentum, IMEC, PhotonBridge, OpenLight, Finetech, Syntel Photonics, Acceloprint, Ligantech, Polariton and Flex Compute.
Lithium, mayo, indium phosphide, quantum dot light, placed right on time. Lithium, mayo,
We'll look at some of the real bottlenecks like alignment, thermal management, process integration, yield and reliability. You may have seen some of the speakers on stage at PIC Summit USA on January 19th. Now that deep dive conversation continues online for 90 minutes. And it matters more than ever. Global tariffs and trade uncertainty are pushing companies to rethink supply chains, from just in time to just in case. And thanks to the support from our sponsors, your attendance is free, but you do need to register in advance to actively participate in the discussion. Now you know who's here. Let's start.
Welcome to the online industry meeting on heterogeneous integration. I see many people who were with me last week in San Francisco. Safe travels, everyone. I hope you all made it home safe and sound. Today is a very important day. Today we are talking about perhaps the most important challenge for us to match the demands of AI-driven companies. We are talking about bringing the best of all the worlds in photonics. We are talking about combining different materials. This meeting is free of charge for all of you because of the great support of our sponsors today: Ligantech, OpenLight, Polariton, Vanguard Automation, Micronic, PhotonBridge, IMEC, Fix, and OE Waves. Thank you very much for great support as corporate member and today for sponsoring this event and facilitating this very important discussion. For many of you, you know how it works. You know how this meeting runs. It's two groups of companies. There is a group of companies who are here manufacturing heterogeneously integrated photonics. And there are companies here who have part of the solution and can actually make the work of the integrators even better than already is. That's why what we're going to do in the next 90 minutes is to match the demands of the integrators with the technology of the enablers and all the people with me in the room. The integrators today are the silicon nitride platform of Ligantech, the silicon photonics and silicon nitride platform of IMEC, the devices, the photonic devices of Lumentum with their indium phosphide single-chip manufacturing, OpenLight offering the entry point of many foundries, including of course Tower Jazz, and the indium phosphide and silicon platform, unique silicon platform from Syntel Photonics. And the enablers are Acceloprint, PhotonBridge, Finetech, Flex Compute, and Polariton. This is a meeting that is made to create value to our corporate members. If you are not yet a corporate member of Optica, join corporate. Optica.org/join corporate. Go there right now, fill the form, and join us because we need you. We need you to continue doing our job. Also, very important, this meeting is part of a long series of meetings, online industry meeting. You can find all of them in YouTube. The next meeting is laser beam shaping on the 10th of February. If you're making optics, micro optics, and you can actually beam shape anything, stay there on the 10th of February. But today is all about heterogeneous integration. And I would like to remind everyone that this meeting is live streaming YouTube. So let me say hello to the YouTubers of the world. Hello, YouTubers. If you have any question, write them in the chat and I will read them in the room. And this is, of course, so valid for the people here with me in the Zoom room. This meeting is as good as you want it to be. You are here to connect with each other. There's 120 people with you in the Zoom room. Use the chat. Write in the chat what you do and what you can do for others and connect. On the next 1 hour and a half, connect with your particular partners, suppliers, and customers. They are all already here waiting to do business with all of you. And now I would like to give the floor to the person who made this fantastic agenda. He's the director of optics, photonics, integrated circuits, and quantum technologies. Coming all the way from Bristol, UK, Dr. John Pugh. The floor and the attention of the heterogeneous integrated photonic community is yours.
Thank you so much, Jose, and hello, everyone. I'm, of course, delighted to be co-moderating today's very exciting Optica online industry meeting on heterogeneous integration in silicon photonics. And heterogeneous integration is no longer a buzzword, but something people are actually trying to manufacture, qualify, and scale. So we've structured this session to start with a real integration partnership. Then we widen out to materials, devices, tooling, applications, and finally, a deliberately different approach. The aim is simple. What works, what doesn't, and what's still missing? What partnerships can be formed to overcome these challenges? I'd like to thank in advance all our speakers for joining this meeting today and being prepared to answer all your questions. So please keep them coming. If you type them in the chat, as Jose said, we'll welcome you to unmute and join the live conversation. So let's jump in with a concrete example. Jeroen Goiverts and from Ligentech and Alex Chikawi from Accelleprint are working together on 3.5 integration using microtransfer printing. Under the collaboration, Accelleprint brings its microtransfer printing, MTP, expertise, a scalable way to place high-performance active components onto diverse substrates, while Ligentech brings its low-loss silicon nitride platform. Alex, Jeroen, please share your slides. The floor and the attention of everyone is yours.
Hi, John. Hi, everybody. Thank you for inviting us for this fantastic webinar, and I'm really looking forward for the discussion from now on. So my name is Alexandre Chikawi. I'm Business Development Director at Accelleprint. I'm going to update on MTP side, and it will be followed by Jeroen at Ligentech, who will update on the progress on their side as well. So MTP, Accelleprint. I mean, I only have 2 minutes. I could talk an hour on that. So I decided to be short. So Accelleprint is the pioneer of microtransfer printing technology. What is MTP? Again, I'll try to do it in 2 minutes, but I thought it would be easier for me to just focus on the benefits of the technology for this particular industry of silicon photonics. So the first thing that MTP brings on the table is that it enables the high volume datacom market. When we're looking at the forthcoming forecast and number of wafers that we're going to need to deliver in the few coming years, what I can tell you for sure is that at least flip chip technology is never going to make it. So that's one aspect. The other thing that MTP brings on the table is that it enables above 400G per lane transceivers. This is exactly, I mean, if you want to reach high bandwidths, what you need is small, thin components, small pads, few parasitics, really optimized interconnects. That's what you need. And this is also what MTP can bring on the table here. And it's also the best material savings technology. As we know, it's all about cost at the end. And MTP is saving and is 80% better than wafer-to-wafer bonding, if you think about the savings for 3.5. It's 60% better than die-to-wafer. And there's another thing which many few people talk about, but where our industry partners think it's a very important parameter. You can reuse the 3.5 substrates. And as you know, there is a big shortage of 3.5 substrates. With MTP, you can reuse and reuse and reuse it. So you're not impacted by that. So this is a very good and important parameter. And of course, it enables low power systems because the placement accuracy today of 300 nanometer enables low light coupling losses of much below 0.5 dB. And we have a roadmap down to 100 nanometer. So in recent years, right, we have a huge amount of development and investment made by our RTO partners like Tyndall Institute, where Accelleprint is actually located. The headquarters are within the Tyndall Institute, but also other RTOs like IMEC. And millions and millions of dollars have been spent to validate MTP technology in the applications, because our partners in RTOs, they have application experts. And thank you so much for bringing that, because without this, our technology wouldn't be where it is today. At Accelleprint, we made the conscious decision to focus on bringing our industry partner to production, because our people are experts in microfabrication. And so when you hear about our announcements, it's mainly focused on production, on everything which has to do with supply chain. And so we have announced back in September 2024 the world's first integrated value chain for HI integration in photonics, and a partnership with XFAB and with Ligentech. And I'm not going to talk more about that, and Jeroen will explain what's the status on that and the progress we have made in the integration of components. We have also, just before ECOC last year, announced that Intel has signed a letter of intent, and together with Acceleprint, we're going to see how we can leverage MTP within Intel silicon photonics manufacturing site. Again, this is about production, and this is really our focus. You will not be successful, I think, in this market if you don't have some footprint in Asia. And therefore, we are also announced that we are joining force with Enostar into the silicon photonics integration. They have high capacities, they already have MTP printers. And so again, the only discussion we have with them is to reach production. And last Christmas, we have announced that Acceleprint is acquiring the tool capabilities back from X-Display company. So actually, it's a know-how and capabilities which is back to Acceleprint. And this is always with one vision and target is to start production as soon as possible. And today, I'm really happy to talk about a specific use case, which is the activity we have together with Seagate Technologies. So Seagate is an Acceleprint customer. They are making and producing hard disk drive using Hammer technology, heat-assisted magnetic recording. And this technology is using a laser. And I'm really happy to say that this is using an MTP laser. You can see here on the little cartoon description that you would need basically a laser coupled to a waveguide, and this is how the system looks like. And the print accuracy and the print requirement needed to build that system are very equivalent to what is needed for any PIC integration that will go next in transceivers. So, and this high yield and high volume production is achieved using an Acceleprint industrial printer. So, so we are really happy to really say that lasers are now in mass production with MTP, and a lot of people were saying that it's still years away, but I would say it was a year before that everything was prepared and it's ready today. So, Seagate won the SPIE Photonics Prism Award just last week on the optical and material components with this technology. So with all the learnings that we have made with this release to production experience that we have gained, we want to apply that to any other type of material sets. Photodiodes, micro-optics, any other components like thin film lithium niobate, and this is what we're doing. And I would leave the floor now to Jeroen, who is going to explain you what is being done and what's the progress of the 3.5 integration onto the silicon nitride platform.
Hello, everyone. I'm Jeroen Gooivaerts. I'm a technical lead for 3.5 integration at Ligentech. You can press a few more times, Alexander. So Ligentech is known for the silicon nitride waveguide platform, but then the topic of today is about specifically our photodetector integration, where we use a microtransfer print technology offered by or developed by Acceleprint. Here you can see just an example of a demo circuit where we integrate a few of these photodetectors, and the snapshot is made right after printing. The next slide, please. Here, so you can see on the left-hand side a source substrate. So it's an indium phosphide substrate full of photodetectors. So as what Alexander was hinting towards is that we can have a very high density integration on the source substrate, making for an efficient material usage. And specifically what's relevant for photodetectors is that For specific applications, you can have a few photodetectors needed, or you can have a lot of photodetectors needed on your target PIC application. And that puts different constraints on the overall yield. So what we discussed together with the component provider is that we want to have this on PD testing capability, so we can, similar to flip chip, assess known good die principle for the photodetectors. And so the component provider supplied this and provided these measurements, and they achieved above 99.5% yield. And then we can kind of select the bad performing devices and filter them out. So on the right-hand side, you can just see a few of the statistics on junction capacitance and dark current or leakage current from the devices. And these are very high performing photodetectors and performing up to spec as what the component provider stated. For the next slide, please. So then after receiving the devices, there's some development effort needed in order to make the devices essentially pick and print ready. So this is what we've been working on in the last year. Here you can see in the bottom image an example of such a component picked and print on top of a waveguide, a silicon nitride AN800 waveguide. And we print the photodetectors locally in a cavity, and then the light is coupled evanescently into the absorption region. So on the top left-hand graph, you can see that the leakage current performs similar as before. There's some slight variation that we identified and that we're working on improving that. And then on the right-hand side, you can see one of the benefits of having these evanescently coupled detectors is that we can have a broadband response of the detectors covering a large wavelength range with good responsivity values. What is not shown here in the bottom image is essentially the final interconnect stage where we connect the printed photodetector to the backend stack of the PIC platform. But that's just a very brief summary of what we've been doing essentially the last year and a half. Maybe if you can go to the next slide, we can just share a little bit on the roadmap. So for the detectors aside, as mentioned before, we started a little while ago scoping the project and negotiating with the suppliers in order to get towards these transfer print ready components. And then over the last year, we essentially received the detectors, made them print ready, and then trialed out, did some development and had some early access runs. And then for this year, what's essentially on the roadmap is to transfer this from the prototyping stage towards the volume commercial offering. Actually, within a few weeks, the first lot will start, and we expect to finish the end of the first quarter, where we combine all the different separate modules that we've been developing on the 200mm offering over the last 6 months, and then put them all together. And then for the detectors, essentially moving forward, the tail end of 2026 into 2027, we'll expand our offering with additional suppliers and also expand the product offering in terms of higher speed for the detectors. And then at a later stage, also expand towards different cross sections to offer, for different application cases. On the SOAs and laser side, given the time, I did not really go into that, but essentially we started a similar activity last year. So here we're still in the prototyping phase at the moment, and here we're targeting the scale up of that activity beginning of next year. And then towards the next slide, this is it from my part. Back to Alexander.
Yes. So yeah, I mean, this is the famous "What can you do for us? What can you do for you?" Right? So, so what you can do for us really is for component makers, lasers, PDs, SOAs, modulators, micro optics. Please, I mean, if you embrace our technology, that will be great. Help us grow the supply chain, trust in MTP, in developing MTP compatible components. For PIC foundries, help us democratize and integrate MTP into your PDKs and ADKs, right? Right now, we have a lot of vertically integrated customers. It's not really necessary for the success and ramp in volume, but to address the broad market, we need this. And please promote our technology there into your PDK and ADK. And in terms of what we can do for you, that's what we call the MTP Alpha platform technology. Those are the services we provide. We can bring your proof of concept to life We can provide custom training on MTP. If you need MTP training, you can contact us. We support your manufacturing partners and your factory to reach production-ready stage, like we did with Seagate. We provide print services. We provide now, since Christmas, last Christmas, the best-in-class production-grade MTP printers. And you have access basically to the largest IP portfolio worldwide in MTP. And I think that finishes the talk, and looking forward for the questions.
Alex, Jeroen, thank you so much. And thank you for preempting the Optica question of what can you do for others and what can others do for you. For those watching, if you'd like to answer any of these calls, please get in touch directly, or I'll be happy to provide an introduction. So we have a couple of questions in the chat. Poonam, would you like to unmute and ask your question, please?
Yeah, sure. So I have a question. You first fabricated device on India's on indium phosphide and then transfer it on silicon nitride. So I have a question. Does your devices are passivated? And how did you passive? Did you passivate before transferring or after transferring on silicon nitride?
Thank you for your question. So to answer, we use a custom tethering mechanism as part of the Accelerant technology portfolio in order to encapsulate the photodetector and make it pick and print ready. And then on the silicon nitride PIC side, we essentially have a standard cross-section, but we use what we call a LOCA module, which is a local cladding aperture opening, which essentially makes a cavity right above the main waveguide. So that opens up this main waveguide for evanescent coupling. And then we use a thin adhesion layer in between, as is typical for this technology. And then afterwards, indeed, we passivate with a final layer to make sure that the photodetectors are sealed and do not move in any circumstance afterwards.
Okay. Yeah, thank you so much.
Great. And Stefan Heinemann from FIX, all the way from Bozeman, Montana. What's on your mind?
Yeah, thank you for the great presentation. I would be interested to just get a rough understanding on what the bring up of such a transfer process, entails in terms of timeline and partner commitments. I would assume that you need special, as Leitensek Jeroen just explained, you need special interface layers and a special run on the PIC side. How about the active component? How do they need to be specialized? How do you qualify lasers/photodiodes?
Okay, so thank you for specifying the question a bit more. Indeed, you're right. So I will not say it's not a challenge to bring these component providers on board. It's a bit of a challenge and requires some time and motivation to see the benefits of the technology. But you also have to keep in mind that a lot of these component providers have already a technology portfolio, and a lot of it can essentially be reused for a transfer print offering. Like for instance, for photodetectors, it can be very similar to already known offerings. I think, the biggest difference, but it could also be almost the only difference, is to introduce this sacrificial release layer underneath the structure. All the other parts are fairly are almost always a bit plug and play from different technology modules that these component providers have. Then in terms on the PIC side, evanescent coupling, grading coupling, different types of coupling, these are not unique to transfer printing. For instance, evanescent coupling, this is also being used for wafer-to-wafer approach or die-to-wafer approach. So also in that sense, for us, it's not really that we have to put a major investment towards developing the platform specifically for this one direction. I think these technology modules can be reused across different integration methods, but it just happens to be the case that transfer printing offers some nice benefits towards scaling and plug and play features for the different material systems that can be integrated on silicon nitride.
Lots of excitement to come with transfer printing, with the partnership with Intel, with the work with Seagate. So looking forward to following to see where that goes. Thank you very much for joining. So let's now zoom out from this concrete example and see how others in the ecosystem are tackling similar challenges. I'm delighted to welcome Philippe Suzanne from IMEC. Philippe leads strategic development efforts that explore heterogeneous integration options, particularly how diverse materials and photonic building blocks can be combined with silicon platforms to unlock new levels of performance and manufacturability. His insights will ground the session in both cutting-edge research and practical integration pathways that are shaping the future of integrated photonics. Philippe, please share your slides. The floor and the attention of everyone is yours.
Thank you very much, John, for the kind introduction. I'll be going through actually a set of different integration techniques for heterogeneous integration. You might see I have been taking the heterogeneous integration in a broad sense and try to see how this applies to integrated photonics. So you might encounter maybe different kind of techniques, and we can discuss later on about the pros and cons of the different approaches. So when we look into what's going on, and I think that was partially depicted by the previous speaker, we have the datacom ecosystem, we have the emerging, and what we do see as you move towards co-package optics, and there's a density of modulators that is increasing, there is a larger bandwidth, so basically silicon might not be able to cut it. And we have on the emerging type of things more the light sources that have actually a variety of wavelengths, so it needs different kind of EPIs, sometimes needs amplification, and the price as well. We have this good old debate that is never resolved about being on chip or off chip for the lasers. Today in datacom, they are favorizing the off chip because it's more serviceable, but it's maybe a sweet spot as well to move the item on the chip. So talking about heterogeneous integration processes, in the next slide, you will see first heteroepitaxy. We have a tendency to forget that, but why would you like to pick up the 3.5 from a different substrate? Why don't you just grow it directly on the substrate? So that's the first thing that I would like to depict. And then you have the different item where we are bringing actually, in that case, I take the 3.5 by different technique to the PIC substrate, and you will end up with different kind of configuration, which I grossly depicted here, but I wanted to discuss with you. What is maybe important when it comes to the manufacturing is that on the first side, we don't need a foreign substrate. We directly grow on the substrate, very researchy today, but there's some good sign that it might work. And then there is a question whether your EPI is coming from an EPI or let's say the heterogeneous, by extension, the non-silicon material is coming from a different substrate and you're going to contact it after you have transferred it, or whether it's already pre-contacted when you bring it to the substrate. As you understood, moving from left to right is more or less the technology readiness level that you're seeing, but it's something you need to keep in mind when it comes to manufacturing. So let's dive into the first one, which is the most extreme, I would say, which is this heteroepitaxy. IMEC has demonstrated with the right reactor that you can actually grow gallium arsenide directly onto a 300 millimeter substrate, and we have been demonstrating lasing. So there is still a lot of challenge when it comes to reliability and so forth, but it's a very promising approach. Pretty much forward looking, but since I tried to be comprehensive today, I just wanted to show it to you. Moving next, I think that was extensively discussed in a previous talk, it's about indium phosphide and thin film lithium niobate by microtransfer printing. We have actually been demonstrating that we can use that technique for thin film lithium niobate. We are actually reaching 2.85 VPIL right now for this kind of device. We expect we will be announcing that. So what is very interesting for us is that we do already have 100 gigahertz PDs actually in the silicon photonics platform. So we were only missing the modulator. That's very interesting. By extension, you can, on the bottom left, you can actually see that we can also bring SOAs on LPCVD nitride. And I don't need to repeat the previous discussion. For us, it's a very interesting approach because it's adapted to scale-up manufacturing. It's already demonstrated on 200 millimeter, and that's a very interesting approach. Now I'll be diverting a bit. So we looked into die bonding. It's very popular as well. There is a lot of enhancement being done. And today, this is actually wafer-to-wafer, chip-to-wafer bonding, molecular bonding is very mainstream on CMOS imagers, on DRAM, and it's also what's going on for the COUPE processes for bringing the EIC on the PIC from TSMC. And we are actually facing different challenges to get there as well if we want to use such approach. First of all is that we are not bonding directly silicon to silicon. So there is actually a first challenge there, which is mainly about the cleanliness of the singulation, as well as the defectivity and reliability that you get from this approach. Still at IMEC, we are looking into this kind of approach as well. And that's what I want to show on the next slide. So this is an absolutely non-photonics topic, but I think it's important that you look what this could mean for photonics, is that we have been demonstrating using the Soitec approach, the imposed substrate. So basically it's an indium phosphide on silicon. And this indium phosphide itself actually is going through the SmartCut technology. And we have been showing that we can manipulate indium phosphide grown on silicon like a normal silicon die. And we have shown that we could use that in that case for a high frequency device. By extension, you can actually see that this would be very interesting as well for other kind of indium phosphide type of technology. Now I'll go into another item, which we have been using more with a focal plane array focus. So we can also perfectly take the 3.5 itself and bond it. Here you can see it's a very large square, so very different use case, for instance, at MTP, and IMEC we're pursuing both. But it's interesting to see that such approach actually has its own merits. And when we talk about integrated photonics in a broad sense, you can understand that if you want to make an array of emitters, that is actually going to be extremely interesting as well. Here in this example, we actually are showing that whether the device, in that case, it's a PIN photodiode, is behaving in the same way before or after transfer. Finally, and I think that was now known for some time, and it's already in production, you can use as well flip chip to bring your, in that case, a 3.5 directly on the substrate. It's actually very interesting because the existing OSAT infrastructure when it comes to plating and die bonding is already existing. And there are use cases where such an approach can be used because it does not require any magnification actually of the starting substrate. You can reuse the lasers, the DFB lasers and so forth that are actually made directly by the compound foundries. So the question is, Philip, you're showing a lot of things, but what does that mean? So what is very important is that each technique has its merits when it comes to the relative area. So what is going to be the ratio of that material you're going to have on the final substrate and the die that you need to pick up. And this is actually here the message is that you do not have let's say an absolute answer to which heterogeneous integration is the best. It actually depends on this ratio. Moving further, if you now look at the industrial reality on the right side is that everything that has to do with silicon bonding is very mainstream in the silicon world, is not actually in integrated photonics, but we do see layer transfer and chip bonding as being, quite well adopted so far. So that's interesting. And finally, and that's going to be a non-decisive, let's say, conclusion from my side is, people are asking what actually is interesting. Where is the optimum? Well, actually it depends on the use case. Usually what we do in IMEC, we look at the throughput. So that's something we don't mention, but throughput is very important for the cost of ownership of the technology. We look also what is the material that you are transferring. You can understand that transferring gas or indium phosphide or very precious lithium niobate is not the same, so you're going to end up with a cost. And as was mentioned previously by Alexandre, the donor substrate reusability is also very important. So on this, I finish and with a non-conclusion, just to tell you that depending on the use case, whether you have modulators, again, medium, and the amount of material that you're going to put on your target substrate, you're going to pick up the best technique. Thank you for your attention.
Thank you so much, Philippe. You mentioned TFLN. That's been very, very popular over recent times. So what are the real bottlenecks for scaling TFLN adoption right now? Is it wafer size, yield, integration complexity, or is it packaging, would you say?
I think that the cost of TFLN is still a major detractor to the adoption of the technology. And indeed, there is going to be different use case. For instance, in the field of pluggables, you only have a few components. So here, in that case, for chasing 400 gig per lane, that might be a very good use case for microtransfer printing. Now, whether people that move to CPU and have way more modulators, we'll have to see actually. So it's really an economical question in terms of manufacturing readiness. I think the heterogeneous integration part is fairly mature because even in labs or in small entities like Gentech, you can actually see quite good yield already. And there is probably another potential challenge is so lithium is a contaminating material, so you need specific infrastructure. If you want to move that to the place that is manufacturing the PIC, then you have some specific contamination, specifically if photonics is made in CMOS fab. If you now are a bit more open and can tolerate that things, that is something, but you need volumes, and it's a bit of a chicken and egg right now. Do you need specific infrastructure for contaminated, corridors? That's actually the big question right now.
And indeed, and today is actually a very timely following the press release of your collaboration between IMEC and Vico, developing a 300 nanometer platform for the epitaxy of BTO, something I think only PsiQuantum could boast up to now. So what do you expect BTO on silicon to unlock?
So from what we know, thin film lithium niobate as a material has the lowest loss, has the highest speed. I think BTO will not be competing that, even though in IMEC we will see what we can do. But what we were particularly chasing with the 300 millimeter work on BTO is first to lower the cost of ownership, because indeed there was, for those who don't know here, if you Google, you will see there is a press announcement between IMEC and Vico. We are actually chasing to move away from MBE as a technique. I cannot say more about it publicly. And to show that it can be a process that can be scalable. Now, the integration of the BTO on the PIC is a subject of research in IMEC, and it will depend on this relative area that I have mentioned. So whether we need to transfer centimeter size coupon or much smaller component is going to be making the decision. It could even be that it's wafer to wafer that is being picked up at the end of the day.
Very exciting.
If the cost is low enough, right? So that's always the same question.
Indeed. Well, congratulations on the collaboration. Very excited to see where it goes. So thank you, Philippe, for joining. We're very excited now to welcome Matt Guzzi from Lumentum today's meeting. Matt brings deep and broad experience in semiconductor packaging and assembly, shaped by more than 21 years of leading complex integration initiatives at scale at Intel. Now at Lumentum, he has been central to aligning photonic component development with real-world manufacturing and packaging requirements, translating high-performance designs into products that can be reliably produced and deployed. Matt, we look forward to your insights on how packaging expertise is powering the next wave of silicon photonics innovation. The floor and the attention of everyone is yours.
Cool. Thanks for the introduction, John. Like John said, I am in the CTO office at Lumentum. I've been there a bit under a year after a pretty lengthy career at Intel. I spent that entire time developing advanced packaging flows and working on heterogeneous integration. Of course, advanced packaging 20 years ago isn't quite what it is today. So I've had a really interesting history, and I think my background is really why I find this topic of today's session so powerful. I've seen the effect that heterogeneous integration has had in the in the semiconductor space, and I see the photonics and optics industry ready to take advantage of those similar techniques and get a lot of the same benefits. So at Lumentum, we are experts across interconnect technologies. We both provide 3.5 components. So individual lasers and our VCSEL platform is widely known. So if you have an iPhone and you unlock your phone with your face, you're using VCSELs. But not only do we bring individual 3.5 components to market, we also do offer entire package solutions, such as our 300 by 300 MEMS-based optical switch. So we really sit in a unique place where not only do we understand the device and the device physics, but we also understand the integrations and taking something all the way to a high volume product. So it's really an interesting place to sit, especially now with where the industry is with the the AI revolution, if you will. And what's really great about AI is the influx, the influence it's having on the market, right? If you're getting a larger model, right? If you're on the latest version of ChatGPT, or if you're training a model, you're going to be pushing your hardware resources to the limit. So you ended up needing to buy more and more stuff. So you've got all this capital investment that's going on. At some point, someone's going to look at the books and be like, well, we need to find a better, lower cost, faster solution to do that, which then drives technology innovation, which then brings those efficiencies and brings those costs down. But once you have the opportunity in operating a lower cost, you go ahead and bring in the next model on, which is going to be even larger. So we're in this cycle where we continually go on, where the AI scaling that's occurring between both the teaching the modules and the inference that's going on is really driving a lot of innovation and really pushing the industry forward. It's really an exciting time to, for me, it was really an exciting time to enter this space to really see how those packaging techniques can apply. At the most straightforward manner, I think heterogeneous integration and advanced packaging techniques are really necessary to allow co-packaged optics to really take the primary seat of being the electrical to optic solution. What we're seeing is that the pluggable optics, that have been common, are slowly being pushed to NPO, near packaged optics, with the eventual target of having a co-packaged optics solution. The benefit is here, as you bring your optic connection closer to your electronics, you get faster bandwidth, lower power, a higher degree of efficiency, but you are trading it off for more complicated, essentially if you burn out a laser in your co-packaged solution, you can't really replace it easily. You're replacing the entire chip. And also just the integration of these devices is much more complex than simply plugging a board into your PCB. But this translation and this evolution of your optic solution from being something that exists on the board far away from your ASICs to something that coexists on the same substrate or even on the same die as your ASIC. It's really enabled by heterogeneous integration and advanced packaging, because you're not going to use the same silicon nodes that you're using for your high performance compute. You're not going to be using that same silicon node for your light source or your photodetectors. You're just not going to do that. That's not going to be a efficient solution for anything. So really, I see advanced packaging really essential here, but I'm actually more excited about the other benefits that these techniques bring to the industry, because this is some amazing enabling. But the power of these techniques and processes go far beyond this. And I sort of see, having seen this evolve at Intel, I think a lot of the same benefits can here. The first is it gives us an alternate pathway to extend a Moore's law type scaling. It's not simply, I don't need to push a single laser faster and faster and faster. I can integrate multiple laser sources, run multiple channels, and get the bandwidth that way. I don't need to be driving a single channel at 400G or 800G. I can find techniques of using several 200 or 100G lasers and get that same scaling but not need to extend my power envelope or push my fab process so hard. And we're even seeing this today with the aggressive growth of optical signaling bandwidth generation over generation. If we were simply being limited by the device physics, we wouldn't be able to keep up with the bandwidth requirements. So we're needing to find alternate ways to satisfy that demand. Also, like I said on the previous slide about co-packaged optics, but this heterogeneous integration really allows us to bring the best solution for each individual component. So you can mix multiple optic technologies, right? So if you need a high quality laser source, you might look at a 3.5 solution. You might be looking at a gallium arsenide laser or a VCSEL or a pump laser. For modulation, you might use a TFLN, right? If you want that high speed modulation, you're not going to do better than TFLN. But TFLN can't on its own. It doesn't generate light and it doesn't have a photodetector, so that in itself is not a complete solution. Silicon photonics. You need to get the light from location A to B. Silicon photonics has amazing capabilities with waveguides and the MUX and DMUX and all the integrated solutions that you can have within a silicon photonics platform. But again, silicon photonics lasers, their performance really isn't always there. They show weird reliability impacts, and it's not going to necessarily be your best solution. But with heterogeneous integration, is you can take these components sort of almost as a la carte menu, right? Like you're at a tapas restaurant, and you can grab the components that give you the best overall solution and the strongest performance, and also the best cost story, and put all of these together within a packaged solution and really give you the best in class overall product by mixing these different technology elements. It's very similar to you would use one, if you're putting memory in a package with a compute core, you're going to use your cutting edge technology node for your compute cores, right? Your smallest possible transistors you're going to want there. Your memory, though, your memory doesn't need to exist on that. So you can use an older, cheaper node and integrate your memory with your compute that way. It's the exact same thought process here. Also, I think one place, and I didn't put this on the slide, but yield improvements. If you're looking to make an array of lasers, 3.5, the yields aren't always great, and you're going to, if you have a 90% device yield for a single laser device, and you're looking to integrate two of those, your yield will drop to about 80%. If you're going down to, if you're going to 4, you'll be somewhere at 60%. So you're taking a cost hit by providing an array of lasers. However, if you can integrate those lasers separately and individually, you can maintain your fab yield and keep that economy of scale and that cost story, and integrate them together in a packaging solution, which will be lower cost than what you would pay on the fab hit. So you can get your 4 laser array, but at a lower cost than a native fab solution. It's very similar by putting two 64 core chips together and getting a 128 core versus doing a native 128 core and getting a fraction of the yield. And then also what's great, especially with how fast the cycle is moving, is by using a chiplet-based architecture or by reusing specific elements that have previously been validated, you can reuse that IP in the next package forward, and you don't necessarily need to revalidate it, or you don't need to redo your reliability data collection. You only need to worry about validating the integration of that with the system, and the individual components you already know are certified and you already know that they work. So this can both reduce your design timeline because you're not needing to do a full chip design, you're simply using this module. But it also can reduce your validation timelines. So you can get a faster time to market and sort of get ahead on that performance curve and get your parts out to market faster. So I find all of these sorts of advantages to be almost as powerful as simply enabling co-packaged optics. Yes, a co-packaged optics solution, something that you can slap into a COUP platform. That's kind of the holy grail right now. And to find that way to mix these perfect ingredients into COUP, that is incredibly powerful. But even at a more basic level, all of these advanced packaging can impact your cost story and your product offerings across the board, and they really open up things that were extremely challenging to do previously. There's a lot of excitement here. This is actually where a fair amount of my personal work at Momentum is based, is trying to apply these techniques to solve some of these sorts of problems. At Lumentum, unfortunately, I'm not quite ready to bring what we're doing to prime time yet. It's not quite ready to be on stage, but we do have one very clear example of some of our 2.5D packaging, and that is our VCSEL on driver. So our VCSELs are our vertical cavity emitting lasers. So basically, this is a laser chip, and this is stacked directly on the driver, which then would be wire bonded to a PCB. But here, you're getting the fastest possible connection between your driver and your laser in a very small form factor, lower power, better performance, and this sorts of module is in high volume production. And I'd say specifically VCSELs, VCSELs are an amazing optical source technology, and we are specifically looking at a lot of ways to use heterogeneous integration to bring VCSELs into different platforms, and how to combine VCSELs with different sorts of chips and different architectures using these sorts of packaging. So while I can't quite show some of our killer apps that we have in plan for applying these techniques, I'm really excited for where it's going, and really the opportunities that this technology is opening up. And hopefully in the coming months, you'll see some pretty cool packages coming out of Lumentum that leverage these techniques.
Thanks so much, Matt, for joining. And I personally cannot wait for prime time and for the big reveals. I'm assuming something big at OFC, but maybe you can't commit to that.
I mean, I'd say that. I think that would be a great opportunity to share something.
Fantastic. So in the interest of time, I'm going to move on. Didn't want to stop you. It's great insights. But so next up is Steve Alliston from OpenLight Photonics. Steve brings a platform level perspective on how silicon photonics design, boundary access, and heterogeneous integration come together in practice. Steve, the floor and the attention of everyone is yours. Thank you.
So thank you, John. So yeah, it's great to be with everyone this morning. I just want to share a couple of slides in the session on the work that OpenLight has done in terms of bringing heterogeneous integration to the market, and explain a bit about some of the applications that we're seeing this technology used in. In terms of who OpenLight is and what we do, so OpenLight is a company that was formed in 2022. So we spun out from Juniper Networks at that point, and our mission in life really is to bring heterogeneous integration, which to our eyes is the integration of 3.5 materials and indeed others onto a silicon photonics platform to the outside world from there as well. And we've done that in conjunction with our partner Tower Semiconductor by creating a PDK that customers can design into with a library of different components for different applications. A lot of our PDK is very much focused towards datacom, but we do have other devices in different bands for different applications from there. So probably about 50% of our engineering time is done to develop components that are added into that PDK that customers can design into on their own, or in fact, with the assistance of ourselves or some of our design partners from there as well. But on top of what is in the PDK, we do have a library of devices that are either coming into it and aren't fully mature and ready for true public consumption, or some things that we could consider to be licensed designs as well. And one thing that we've done over the last couple of years as we've worked with the companies, we've come to understand that the ecosystem is incredibly important from this as well. That our ability to generate a PDK is not really a successful market solution unless we have the great support of not only the foundry partners, but the in-feed material from the Indian phosphide fabs, support in the EDA tools, where we have great support from the community, including Lucida, GDS Factory, and Synopsys. But one thing we've also started to do is increase the engineering offering to enable things like wafer level test and backend services as well. So either in conjunction with OpenLight or independently, customers are able to use this technology to create their designs as is needed. In terms of what we believe heterogeneous integration is from our perspective, it really is, as I mentioned, wafer scale integration of 3.5 devices on two silicon platforms from there as well. The way it works is that we take wafers at the tower fab, we pattern silicon and silicon nitride waveguides, and then we selectively prep areas for bonding of bulk epi material from there as well. Now, it's important to note that these are not devices at this stage. This is not a very accurate placement, and we would typically do one placement of a different type of material, which will eventually become multiple devices as it passes through the process chain. What this enables is basically a very high throughput of bonding and very high yield, as mentioned by the previous speaker. If your yield is not high, then really the economics of this technology do not work. And a lot of the effort that Tower especially and our bonding partners have made is to make sure that this step is very, very high 90s in terms of yield from there as well. Once those chiplets of different types of indium phosphide material are bonded onto the silicon, the substrate is removed from that to make it easier to process in a foundry environment. And then we are processing both the indium phosphide to put waveguides, tapers, electrical contacts onto those devices without impeding and destroying the waveguides underneath that from there as well. And this is really when they start to become devices. And because this is done at wafer scale using photolithography, the actual alignment is basically as tight as the photolithography allows you from there as well. And everything is done at the wafer scale as well. So it typically will be creating thousands of devices in a couple of different steps. Once those devices are created on top of the silicon, they're then encapsulated in a thick layer of silicon oxide with a metallization layer on top for either contacting out to wire bond pads or for copper pillars for flip chip assembly from there as well. And what you get at the end of the process is a wafer that looks and smells and tastes like any other silicon photonic wafer. So it can go into a standard OSAT flow from there as well for test, for burn-in, for singulation, dicing, backgrounding, and polishing without any need for special handling just because it's got indium phosphide material in there. So why do we do this? Well, I mean, obviously there is an economic argument for doing this as well. It allows customers to become truly vertically integrated and to buy a single SKU direct from the foundry gates with no markup to get the lowest possible cost from there. But technically, as previously mentioned, different material systems have different advantages. And by pushing those together with very high coupling efficiency between the layers, that allows us to get to a point where we can have very low laser output power, very low current, and we can have a different classes of modulators that are compared to a pure silicon type processors. It is very scalable in terms of production, in terms of test from there as well. And just an example of some of the devices that you can make on this, on the bottom left-hand side is a DFB laser. This is done by writing the grating into the silicon layer and then bonding an indium phosphide gate medium on top of that. Other laser structures are possible. The one in the middle is a full band tunable laser that we offer primarily now for sensing applications and telecom in both O and C band. And you can also make some very high power SOAs from this as well. We have a roadmap up to 20 dBm in both O and C band to support different applications. In terms of the contents of the design kit, it is not just active devices. It does include all of the passive devices as well. And that includes ways of getting light on and off chip using either grating couplers or spot size converters with different mode field diameters, waveguides in both silicon and silicon nitride and transitions between that, and passive components, including directional couplers, MMIs, BMMIs, polarization components, control components, and resonance structures based on ring, Mach-Zehnder, and AWG. And there's also design guides as well so that customers can build their own passive devices. But on top of that, there is a library of active devices that are either represented as cells, or if your EDA tool can handle it, in some instances, P cells as well. So by changing the physical properties of the device, you can change, for instance, the gain or the output power of an SOA, and that's reflected in the model that goes into those tools from there as well. The current list of devices that we support in terms of laser sources, as I mentioned, is the tunable and DFB lasers from there as well. DFB lasers are currently targeted for datacom applications, so are primarily available in O-band and CWDM, but we are starting to do custom designs now with either DWDM spacings or different wavelength bands, depending on particular application needs. Both of those lasers use an SOA is the heart of the device as well, and we offer that as a standalone device with a parameterized cell, again in both O and C band for different applications, with different output powers and different gains for depending on the circuit needs. And then for modulation, we have very much concentrated on electroabsorption modulator rather than a Mach Zehnder. We like the electroabsorption modulator at lower speeds because it can be driven single-ended and look to the outside electronic ecosystem as an EML. And now we're getting to higher speeds by making the device shorter and reducing the electrical parasitics. We're able to extend the bandwidth of that into the 100 gigahertz range, making it suitable for 400 gig PAM4. On the receive side, again, we have photodiodes based on indium phosphide, high speed using a dedicated epi, again, with similar sort of bandwidths to the modulator. And then we monitor photodiodes using side corners of gain epi primarily to prevent you needing to put a specific deposition down just to create a monitor photodiode from there as well. So here's a couple of examples of different devices that you can make from this. These are what we call reference designs. So these are things that we have done using our own technology to either prove it out and to show that it works, but also to be able to supply this as either samples or GDS examples to customers in the pluggable module type environment. We're currently sampling to select customers the DR8 version, the 2xFR4 version of that using the CWDM laser is in fab. We also have some early samples of a 3.2 terabit version, which is very similar device from there as well, just taking advantage of our ability to increase the modulator bandwidth without changing any of the other designs within the chips from there as well. All of these devices use a number of lasers, typically 4 SEAMs and SOAs in the instance when the path loss is too high to meet OMA targets from there. They're all broadly the same size. They're about 5 by 7 millimeters in dimension and typically consume between 2 or 3 watts total power. And this is a device that can be flip chipped onto either a substrate or a substrate like PCBA, as you can see in the top right illustration, which is an EVB that we put together for demonstrations in conjunction with a driver from Semtech in this instance. And that's a complete integrated transmit solution from there as well. And you can see that the quality of the eye, and this is an LPO type configuration in conjunction with a max linear DSP board, as you can see the setup in the middle, is nice and clean and open, and we can happily exceed OMA targets with this technology from there as well. And just to focus on really one of the advantages now as we moved from, as the previous speaker said, from pluggable to the CPO type format. And that's the ability of the modulator, especially with to scale up to the 400 gig demonstration. As of last year, we demonstrated the first 400 gig eye, which you can see on the right, with a modulator bandwidth that had just around 85 gigahertz S21 parameter. We're now working on devices and we have samples in excess of 100 gigahertz, and we have a roadmap to increase that up to 110. And this is a very, very short device. The intrinsic device length is less than 100 microns long from there as well, which means some of the challenges that we're seeing in CPO, for instance, in terms of just power consumption and physical size of devices with other material structures, don't really apply to indium phosphide from there as well. And then finally, although AI is, of course, the hot topic, there are other things you can build out of silicon. And the other area that we've looked at and have partners working on is FMCW. So FMCW LiDAR is a great technical application for both automotive and other applications. It has great range. The tolerance to interference is compared to time of flight or flash solutions is much greater. And one of the side benefits is with FMCW, because you can use the phase properties of the light, you can significantly reduce the amount of digital processing that you can do after that. But FMCW requires things like very narrow line width tunable, fast tuned lasers from there as well. And that's the devices that we can build in silicon from there as well. And then by combining that laser either with or without an isolator and then a splitter array and an array of SOAs with the PBSRs, you can create something like a single chip FMCW type sensor. So the example here in the top right is something that a partner has built. It's a 10 by 10 complete FMCW LiDAR chip. This actually has a laser on board as well from there as well, although other solutions use off-board lasers from there as well. And similar to the data compics, this is something that you can be flip chipped or wire bonded into a package as well. And it's a very compact, thermally stable platform for a high volume application. So hopefully that's given you an idea of what the offering and some of the applications we are. And again,
Steve, thank you so much. That was a great presentation. Very well summary. You actually kept yourself in time, for which I appreciate very much. But Steve, here there is a question for you and for Matt, which is very clear. All of you presented the integration of light sources into silicon. Steve, you presented the DFB lasers, and Matt presented VCSELs. So can we clearly tell the customer what is the short and medium-term solution for bringing heterogeneous integration of 3.5 into silicon for light sources? Steve, go ahead.
I'm sorry, Jose, could you repeat the question, please?
DFBs or VCSELs, what is the best solution?
It really depends on the application. I mean,
It always
as
does.
Matt said, I mean, for facial recognition, VCSELs are a great solution. Not so great for 2-kilometer datacom.
Matt?
VCSELs, of course, work very well for short reach. DFB lasers are for longer reach, and then for other applications, narrowband, high-quality tunables are there as well. So the intent of the technology platform is to offer a platform where different devices can be integrated into that.
Yeah, I agree completely with Steve. Different applications have different requirements, and different laser technologies suit those best. So there's no one size fits all answer. It's about having a platform that's flexible, that allows you to integrate the ingredients as you need to get a product that meets your performance requirements.
We all want to have key applications for each technology, but in my opinion, right now, we have a huge challenge to tell the industry, which is, can we remove the external laser for CPO modules, or do we have to? I would like to ask Doron Tal from New Photonics. Doron, we are talking now, you are pushing also near package optics, NPO with the external laser. In your opinion, is this a short-term intermediary solution until companies can provide a VCSEL-based CPO or heterogeneous integration of a laser powerful enough for CPO? Or is the medium or long-term solution already NPO?
Yeah, I think NPO is starting now. It's just a more pragmatic solution because people are looking for serviceability around laser integration. I think that heterogeneously integrated circuits are ideal for NPO because they offer that serviceability angle. Maybe not at the high density that CPO is demanding, but definitely near term and midterm, and perhaps even longer term, because we can evolve the heterogeneous integration, which is, all the speakers here offered fantastic solutions. And this is really the beginning of the cycle. So I imagine with innovation and tighter integration, we can make near package optics last probably a lot longer than we envision.
Daron, congratulations on what you are achieving with New Photonics. I can't wait your next milestone at OFC, but stay tuned because the next speaker provides a technology that is very relevant to what was just presented by the previous speakers. We are talking about photon bridge and the integration of indium phosphide on silicon in a very different manner with passive alignment, the definition of pure semicon-oriented heterogeneous integration. Thank you very much, John Anderton, from here all the way from beautiful Eindhoven. The floor is yours.
Very happy to be here, share an update on what's happening with Photon Bridge. Maybe if you've not heard from Photon Bridge before or know who we are, just let you know who we are. It's a relatively short presentation today. So this is going to be the 30,000 foot view. Hopefully there's lots of questions. Hopefully there's not enough time, but my contact details are there at the end. Please reach out, challenge, ask questions. And I'll give a shout out at the end for where we would love to hear help and support from the Optica community. So what am I going to talk about in the couple of minutes that I have? Bigger is better for the AI nervous system, or why Photon Bridge is the heterogeneous platform built for manufacture. That speaks to where we see our value in the market, how we see the market evolving, where our focus areas are, and what our heterogeneous platform is all about. Hopefully I can do this in the time available. AI drives bifurcation. This is kind of how we see how the market evolving. We think CPO is happening, and we think CPO is really about connecting the brain of AI. And this is all about density, as several people in the preceding presentations have talked to. So I won't go on this again. It's all about density and high bandwidth density. But you need the nervous system. You need to connect to the physical world. And this requires very different things from integrated photonics. Over the short term, over the next 3 to 5 years, we believe it's going to be all about external light sources. Our platform scales to integrated light sources next to CPO, but in the short term, 3 to 5 years, this is all about connecting to the physical, providing light sources for infrastructure, for powering the connected brains, the CPO engines. But it also scales to FMCW, LiDAR, and all sorts of things. But this is more about density versus power, and where we focus and where our platform really shines is on the right-hand side. And as mentioned, AI will be powered by light. We see the data rate going up. We see the transition to co-packaged optics. And as Philippe from IMEC mentioned, we believe there's going to be a transition to multicolor external light sources. This is happening over the next 2, 3, 4 years, something like that. We believe that the value for heterogeneous integration is really how you integrate all these lasers, integrate all the multiplexing of those lasers on silicon to provide it in a scalable, manufacturable way within the same pluggable device or within the same serviceable and removable device. And to do this, what do you need? You need a platform that's designed for high power, high yield, and low cost. And it needs to be OSAT compatible, heterogeneous integration. Our platform does this. It enables any device to be connected heterogeneously onto a piece of silicon. So our process is material independent. We can support indium phosphide, thin film lithium niobate. We're doing quantum well lasers today, but it scales in our roadmap to quantum dots. It includes high-speed modulators, laser switches, isolators, everything. All can be combined like a Lego. All these things need to be manufacturable and to handle power. So if you look specifically at the multi-wavelength light sources, one of the things about our platform is that we use large waveguides. They're 2-micron waveguides. This means they handle the power and they are robust to process variation and tolerances. That means you can build very high-yielding manufacturable AWGs and MUXes. We, of course, support wafer-level packaging. It's die on wafer. The big thing about our process is that it's OSAT compatible. All the placement of the actives, for example, the lasers, are done passively aligned. I'll come back to in the next slide what that means, but essentially we can resolve 2 to 3 micron placement accuracy at a flip chip bonder in an OSAT. So we don't believe flip chip bonding is dead, by the way. All of this is resolved to effectively 100 nanometer optical alignment. Wafer level packaging, we also have in our roadmap a path to local hermeticity using no-gold boxes. Now, one of the things that we're acutely aware of, any heterogeneous platform is only valuable if you provide the capability to get the light on and off that platform. High throughput fiber assembly is as important as the ability to combine indium phosphide on silicon in a manufacturable, scalable way. So as part of our roadmap, we're developing a passive, efficiently coupled to SMF with integrated spot size conversion fiber attach capability. And anticipating the question at the end, John, the Optica community, how can we work together? How can we get the best value from everyone? If you're working on fiber attach, if you're working on advanced packaging and want to talk to us about how we can partner together to accelerate the roadmap in terms of fiber attach, we'd love to talk.
Thank you very much. And coming all the way from Eindhoven, they provide with passive alignment. They can integrate indium phosphide on silicon. That is great, John. But for that, you will need...
There's the trick for how it works. But I see I've run out of time, so thanks for keeping me honest, Jose.
Thank you very much. And that is exactly the secret here. We want to provide a passive alignment solution for indium phosphide on silicon. And look how the chip comes into the waveguide. To do this, we need equipment. To do this, we need equipment for passive alignment. And here, John Anderton, we brought you the best one in the world. Let's go to Berlin and meet Travis Scott from FineTech. Tell us how your equipment can help PhotonBridge.
I'd just like to thank Optica, Jose, and John for putting this together. It's always an extremely valuable meeting. We take a lot away from it. And thank you for the invitation to speak. So at FineTech, we manufacture flip chip die bonding equipment. We also offer tailored solutions for getting your prototype into production. So we go all the way through technical technical consultancy, getting your packages built in a demo lab or getting it into systems to get it built in the equipment that we sell. And then we also ramp that up into production at OSATs, at offshore manufacturing, CMS and EMS facilities, for example. So our philosophy at Finetech is to go from prototype to production. So our equipment starts at tabletop flip chip die bonders all the way to fully automated production equipment. Currently, our most accurate system is qualified for 0.3 micron at 3 sigma, but we're trying to improve on this and push it down. Like you said, we need to get to about sub 100 nanometer for a lot of this wafer level packaging equipment. We're also trying to bring a system to market within the next 1 to 1.5 years that's focused for chip to wafer bonding. And we're trying to maintain this very modular die packaging approach that we've always maintained at Finetech. And this is where you can pack various different bonding technologies into a single die assembly device. Here are some examples for some heterogeneous applications we've seen over the past few years. Because of the difficulties with heterogeneous integration, 3D packaging, vertical integration, you're always fighting, the reflow temperature or the bonding temperature of your previous bond layer. So if you're stacking, indium on gold, gold on ultraviolet curing to get various different functionalities from these various different chips for the heterogeneous integration, we can offer all of these bonding technologies inside of an extremely accurate passive flip chip die bonder. So if you have any questions, if you have any challenges with your packaging or your die bonding processes, please come and speak to us at Finetech. So the question from Optica is always, what can we do for you and what can you do for us? What you do for us is by coming to speak to us, showing us these challenges. We take so much away from these technical discussions with customers because it shows us, the challenges that the market is facing, what we need to develop to get, in front of the market to keep up with what's happening in production. And what we can do for you is offer 30 plus years of experience in die bonding and die packaging, and a fully tailored custom solution for whatever challenges you might be facing with your packaging. Thank you very much.
Thank you so much, Travis. Some great work as usual. So this is a meeting about heterogeneous integration. So as more materials are introduced, we've heard about 3.5s, TFLN, BTO, and we will hear about metals. And in your experience, where do thermal mismatch and mechanical stress show up first in the assembly process?
This is quite a difficult question with packaging because it bridges so many different parts of the assembly process. Like if you're bonding a laser to a carrier, if you're bonding a large chip to an interposer to a PCB, if this is done with indium or gold, there's so many different variables that can come into it. So it's a very difficult question to answer. But what we try to do is offer as many different paths to fighting those challenges as possible. So we offer, for example, like heating from the bottom as well as from the top. This heating from the top and the bottom can be done at different temperatures, different ramp rates, to try and match those CTE mismatches in your bond layers. We've also integrated laser bottom heating to get extremely fast ramp rates, extremely high temperatures, to move away from like traditional resistance heaters that take a very long time to heat up and cool down. And this keeps your thermal stress extremely localized around small chips. So yeah, it's a very difficult question to answer because the challenges could be infinite within the industry.
Great. Well, if you think Finetech can help you, please get in touch with me. I'll be very, very happy to provide an introduction to Travis. So thank you, Travis. To bring this discussion up the stack, we're pleased to welcome our next speaker, Matt Crowley, CEO of Syntel Photonics. Matt will share the application and product perspective, drawing on Syntel's work translating advanced silicon photonics and heterogeneous integration into deployable systems, where performance, packaging, and manufacturability all have to come together. Matt, the floor and the attention of everyone is yours. Thank you.
So thanks, everybody. Heterogeneous integration is a great topic for me. It's clearly core of what Syntel does. So we're going to talk a little bit about the platform, a little bit about the product, and then a lot about the application and some of the view we have. We're a pretty focused company. We like to joke we're laser focused. And our first product is targeting multi-wavelength external light sources. We call them smart external light sources for AI data centers with an even more focused target on scale-up networks. So what is SHIP? SHIP is our cool little acronym for Heterogeneous Integrated Photonics. We don't have a theme song yet, but I was inspired by the Optica one, so maybe we'll build one. Really what we bring is a heterogeneous integration process that uniquely leverages standard silicon photonics. So working with our partner at Tower Semiconductor, we don't actually have to modify their base silicon photonics flow at all. We simply post-process 3.5 into that base flow, which has a lot of advantages for supply chain scaling and things like that. Heterogeneous integration is great for performance, for density, for reliability. It eliminates a lot of failure modes, and of course, it's scalable to huge volume. So talking a little bit about the process itself, we start with standard silicon photonics. And so, block number one is what we get from our foundry partner. What's nice is from this, we have a lot of IP blocks available that we don't have to redevelop. Our partner can know that any CapEx they do into standard SiPho for a normal transceiver, for example, can also be used for our process. So it's a great business model for them. It allows them to invest confidently in their own capacity. And from that, we have a lot of standard things. We have this, waveguides, photodetectors, external couplers, and things like that that we kind of get off the shelf from our partner. The last part of the process is what is unique. And this is technology that originated at CA Leti with our founder, Silvio Menezes, and has actually really been developed inside Syntil into a commercial process flow. I, didn't really put timeframes, but right now we are running hundreds of wafers. So we did a fundraise at the end of last year, and we're kind of entering initial low volume production, sort of more focused on optimizing yields and such rather than fundamentally changing the design or process flow. So the first step is we call backside on box, is we take the silicon photonics wafer, we flip it upside down, we remove the handle, and we bond it to a new handle. So we've effectively flipped the wafer upside down and expose the oxide layer for bonding. In the next step, we do a molecular bond of indium phosphide dye. These are not yet processed into lasers. It's our own epi stack that we purchased from third parties. And we bond it over the waveguide where it's going to evanescently couple into the silicon photonics. What's nice about this is a couple of things. One is that the laser frequency is determined by the grading that's made using advanced photolithography. So we have extremely high level of precision and control over the geometry of the laser. We also have high repeatability. So we're basically doing lithography. So we basically, every laser on every reticle is going to be the same. It's not written, nothing's moving. It's quite consistent. In general, bringing, let's say, advanced semiconductor process capabilities into this has overall been very helpful to the process. Critically, we also don't have to worry so much about alignment tolerances with this particular process flow because we're doing the definition of the laser post-bond. And so even if the alignment's off at this phase, which it's actually pretty good, it doesn't actually matter very much. And then in the fourth step, we actually fabricate the laser. So we basically take that bonded die that's made out of an indium phosphide stack, and we etch in lithography and define the laser. Then we passivate everything, we connect it, and voila, you have your laser die. Our first product, which we've talked about, is I think we've really focused on the external laser source as our first market. I think as a startup, you have to focus on a first market. And if you're a startup developing both a novel process flow and a novel design, you have to push your first process flow through full qualification and your first design through full qualification so that you now have a platform on which you can launch many, many products. So our first product is actually going to be an 8 wavelength external laser source. Our customers, were interested in 8 and 16. Now they're thinking about 8 as the first step, 16 as the second step. We've built both. The next spec is extremely important, which is you have to have very precise frequency spacing. So it's not just the absolute distance, whether it be 100 gigahertz or 200 gigahertz or 400 gigahertz between channels. What's actually critical to be able to work with the microring resonators that our partners' companies are using is that the laser can't be too far off. And I like to think of it like if I'm trying to shoot a target, the micro ring can pull a little bit, but if your laser is too far off, it's not going to hit the target. And you think about over time, temperature, and millions of units, you need to have that precision. I can say not only do we have great accuracy off the wafer in this spec, but we also have a built-in feedback system and a custom ASIC that we developed in 65 nanometer TSMC to have a complete system that not only has great process control, but also better than that. And so no AR coatings. So yeah, 20, it's yeah, that's correct. So no AR coatings, no current through the grating, high power. Right now we're shipping 10 milliwatts per fiber per wavelength. We have our 20 milliwatt design in fab. And it's pretty efficient, so that's something we have to measure over time. And we have multiple fiber outputs per module, so we are actually also making a module where we can put potentially multiple PICs and our own custom ASIC, and have a complete system that we can provide.
Matt, allow me to interrupt you because I cannot. This is a huge result. 20 milliwatts per wavelength. This is fantastic. Which is the key application that this is a paradigm shift for?
Well, the amount of power per wavelength is really just, I think we're kind of hitting some hard limits because we even had to custom design our ASIC to even pump that much power. And I should say that's not yet shipping. That's a design in fab. So the reason people want more power is because they want to be able to use splits to basically run more channels. So there's two characteristics. One is it's not that our laser is necessarily higher power than other people. It's that we have less attenuation getting from the laser to the fiber, I think is the key thing. So there's other lasers out there that are higher power.
Let's see how we could make a design for that particular platform, and let's see which partners they could actually enable that. Allow me to give now the floor to Philippe Couto. Philippe, thank you very much for joining today from Flex Compute. I am really amazed with what Syntil Photonics is doing. I really am for many, many years. Philippe, can you tell us a bit about Flex Compute and how can you help companies like Syntil and all the previous ones by offering your platform to them? The floor is yours.
Yeah, absolutely. Thank you. Let's just share my screen. Pleasure to be here. So here's Flex Compute. What we provide is tools for simulating and design photonic circuits and components. So I believe you are a little bit in the other end. After you address the process of integrating the many materials, we are in the process of understand how the device will behave and providing tools for that. And I believe a great advantage of Flex Compute is that we actually have modern softwares and modern algorithms that work natively with GPUs. So we can scale our simulations very much. So we can run pretty large models that could not be run before in CPU workstations. So it's very fast and very scalable. But for the integrated world, when we need to put many things together, work with many physics, speed and scalability is just one part of the process. We need actually a full solution integrated to deal with complex problems. So I would like to showcase here this interesting example. This is inspired in a paper where the authors, they created a electro-optical modulator based on a silicon waveguide. So the idea is that we have a slot silicon waveguide and we fill the gap with a polymer. And you create some process in the polymer to induce the electro-optical effect in the polymer. So you can modulate the optical field in the silicon waveguide. And to design and understand this device, there's many steps. You need to carry out the chart simulation to solve for the DC fields into the polymer. You need to solve for the RF fields that will modulate your optical signal. You need to couple the RF fields into your optical waveguide. You need to run optical mode simulations, considering both the RF simulation, the RF fields, and also the doping in the silicon. So you need to put everything together in order to understand this device. And this is what we offer. So we have many tools that working together to fully characterize the device, this design in a single workflow. So the idea is that you have a single workflow and the engineer just needs to take care about the problem in hand and don't need to wait a lot for run this model or waste too much time integrating with different tools. And once you have a component, after some point, you need to put everything together in a circuit. And for that, we also offer Photon Forge, a very powerful tool for photonics circuit design and layout. And the idea is that you can integrate with a given foundry technology, which allows us to, after create our 2D layout, we can automatically create 3D models from our structure and carry out circuit level simulation and fully characterize our chip. And at the same time, exploit the integration of our solvers and the speed and scalability. Well, I believe that's it for now. If you have any questions, I'm happy to answer. Thank you.
Thank you so much for that. It is so great to have the concept support of flex compute and how you are helping so many foundries. Philippe, stay tuned because the next one is perhaps what I am most excited about this meeting. The company Polariton keeps breaking records when it comes to high-speed modulation year after year. Stefan Koch from Polariton, thank you for being here with us. You had the honor for being the closing speech. Tell us what Polariton can do, and then in 1 or 2 sentences, tell us which partners you can work with after this meeting. The floor and the attention of everyone goes to Polariton.
Thank you, Jose. Hello, everyone. My name is Stefan. I'm from Polariton. The best for last? Well, 2-minute pitch.
Always.
2-minute pitch from myself. I will be very tight. So high-speed modulation is essentially a race of the materials. And this is data from Light Counting that says by 2029, all platforms will be there in the market. Well, silicon photonics will be well positioned in various forms, monolithic and in heterogeneous forms, no doubt. But in a way, it's integration of materials. And the material we integrate is polymers. And this we call plasmonics. This is a post-processing step done on silicon photonics. And the big advantage or the big takeaway from this way of doing it, because this is a very simple process step. We have no complex layer stacks. We have one redistribution layer. We have one material integration step, and then the passivation. And the proof of concept of that is with silicon, 200 millimeter silicon done from IMEC, which we have made a press release towards the end of last year about the performance. And the performance is high at any will. Maybe there are other fastest modulators in the world, and the frequency response of a modulator in this specific plot is flat until 100 gigahertz. And what you see is the impact of the test and measurement instruments, the AWGs, and maybe and that makes the entire system performance. And the effect that we are dependent at the end on faster electronics or driving circuitry makes that the current published eye diagrams are maybe not better than the one from Stephen. Nevertheless, we know how to make them improve them better, and because of the driving electronics. And so this is possible because our devices are in the micrometer dimensions. And what can be made small can as well be made power efficient because you have to switch less energy. And this becomes a fantastic value proposition. It's not about going as narrow or about going slow. We can do fast and wide at the same time. And this is the value proposition for onboard optics, co-packaged optics, and any other variants of heterogeneous integration. So what can you do for us? If there is anyone that can help us in doing encapsulation technology, is something that I would be willing to have a talk at any point in time. Why is that important? It's one of the processing steps. Does Polariton not have that one? Of course we have that one, but better encapsulation will permit you to follow cost curves and all what is needed for being in production. Thank you so much.
Stefan, you finished the game, you defeated the final boss because you don't go narrow and fast, you don't go slow and wide, you actually go fast and wide. But you just said something very interesting. You are making devices now. Is that the new business plan for Polariton to be a device manufacturer?
Well, whether it's new or not, plasmonics it's a device. You're right. It's a PIC. Now we can do a PIC with by choosing our own silicon photonics vendors, but actually this is integratable into any silicon photonics process, baseline process. In that sense, it's a post-processing. And yes, well, what we can do for you, we can provide you faster modulators.
For all the packaging companies in the room, if you are brave enough to package an 800 gig per lane chip, Polariton is a fantastic partner. As I said, this is the one to watch. I would like to thank everyone in the room. Allow me now to close the meeting for the YouTubers, and then we can have a private discussion to follow up on the main leads of the event.
This is our